This is Math 261, and this is section 11.6 on surfaces in space, and this is part 2. And we want to see, how do you tackle the questions of actually given an equation like this one, match it with its graph. Well, in this particular case, that form that we're given matches one of those 6 that is in the table in your book. And so these questions are very, very heavily dependent on that table of equations and the shapes. So I'm going to jump down to that, but keep in mind now, in this equation, everything is squared, x, y, and z. Everything, there's plus, plus, plus. There's plus out here, and it's equal to 1. So remember that. So here we are in the table in the book, and we see that it does match the first one, the elliptic cone, because of the form of the equation. And that's what these questions are really all about. It's kind of big picture. You're not digging deep into plotting points or anything like that. You're doing it based on the form of the equation and the forms given in this table. So question 1 is going to be a shape like this one. Here we are back at question 1, and based on what we just went through, this would be the answer. Now for question 2. Now this is question 2, and this one doesn't, the first one was ready made. It matched what was in the table directly from the get-go. This one, that's not the case. We spent some time looking at the table in the previous part, and if you went through that or you look at the table, nothing quite matches this one from the get-go because it's equal to -4. There's nothing in the table like that. It doesn't say equals k or anything. They say equal 1 or equals 0. Or they're of a different type where one of the variables is not squared. So all the variables are squared in this one. Okay. That does cut it down to 1 of 4 possibilities. But the main thing that's going to help us is to make it equal to 1. Okay. It's equal to -4. And that's not how they are in the table. As I said a few times, this type of question is very, very table based. Now, how are we going to make it equal to 1? Well, this is -4. We don't want it to be -4. We want it to be 1. So we'll divide by -4. And then we have to do it throughout both sides of the equation, so every single term like that. And so we get that, and when we divide through by -4, -15x squared over 4 plus 4y squared over 4, and there the 4's are going to cancel, minus 15 over 4 z squared equals 1. So this is looking more like what's in the table type of equation. But terms like 15x squared over 4 are not what we see in the forms of the equations in the table. It's always x squared over a squared or z squared over c squared type of form. Okay, so that's the next thing to think about here. And what we want to do there is, all because of the way they are in the table, over a squared or over b squared, we want to manipulate a term like this, 15x squared over 4. But first off, that's equal to x squared over 4 over 15. Now that's very much a backward step to what you'd ordinarily do. So let me show you. What you'd ordinarily do is you would have x squared over 4 over 15 maybe, and you would go, that's x squared over 1 over 4 over 15, and then you would keep change flip, if you remember. It would be x squared over 1 times 15 over 4. And then you could see how that's the same as 15x squared over 4. Okay, so after that backward step, then again in the table, equations like this, they're all over a squared or b squared or something. So we want to take it to that level. So if we square root 4/15, we get 2 over radical 15 in the parentheses down here. squared would give us the 4/15. And so with that kind of work on this equation over here, we'd come to something, it would come to this. Negative, that'll just stay out front, x squared over, like this now, 2 over radical 15 squared plus, I'm going to write it as y squared over 1, just so it matches the way things are in the table, minus third term, much like the first, but it's z squared over, same numbers, so it's going to be 2 over radical 15 squared is equal to 1. Okay, now it's really, really close to how things are in the table. But in the table, it's going to be the positive term coming first. Then I'll write the minus x squared over 2 over radical 15 squared minus z squared over 2 over radical 15 squared equals 1. So the reason, the purpose for that last step is just because I know in the table, as long as I'm remembering it right, that right there is going to match exactly the form of one of the types of surfaces, and then we'll be able to match it up. So let's remember what we have here. Y squared over, we could call this b squared, because it's 1, minus x squared over a squared minus z squared over c squared equals 1. So we have a plus and minus situation, plus minus minus situation, and equal to 1 situation. Now, let's go down to the table and see what we can see. The type of surface with an equation that matches what we just manipulated our equation down to is this one, a hyperboloid of 2 sheets. Now remember, the variables are arranged differently. This is as given on the table, z squared over c squared minus x squared over a squared minus y squared over b squared. The variables can be arranged differently, but it's that form that matters. This is a plus minus minus situation equals 1 situation, and all the variables are squared. And so in our example 2, we have a hyperboloid of 2 sheets. And then the last step, once you know that from the table, is to pick out from these pictures here the one that is a hyperboloid of 2 sheets, which is this one. Now our third question here is this particular equation, y equals 4x squared plus 9z squared. It's a little bit different because in the previous one, starting out, there was that equal to negative 4, a term without a variable. But in this one, that doesn't exist. Each term contains a variable. So this is going to be, for that reason, equal to 0, 1. So we want to rewrite it so it's equal to 0. Y squared minus 4x squared minus 9z squared equals 0. And then kind of play the same sort of game of putting things in denominators as we did before. Like that, y squared minus x squared over 1/4 minus z squared over 1/9 equals 0. It seems an odd thing to do. It is a bit odd because it's backwards to normal. We're taking 4x squared and writing it as x squared over 1/4. Whereas usually you'd be starting with x squared over 1/4. And then you'd be thinking like this, x squared over 1/4. Okay, keep x squared, change to multiplication, and flip that. So I'd have 4 over 1. X squared times 4 over 1. That would be 4x squared. Okay? And that's kind of the normal direction of it. But here we're going sort of backwards, starting from here and going to there. But there's a method to our madness. The purpose, because of the way the table is given to us, is the reason. And then lastly, in the table, the variables are all over top of things squared. So this would be y squared over 1 squared. This would be x squared over 1/2 squared minus z squared over 1/3 squared equals 0. Now, with that, in that form, we should be able to match this equation with one of the equations in the table, and then figure out which graph it is. So let's remember here a couple things. All squared equals 0, and there's a plus and a minus minus. So remembering those things, coming down to the table, here I'm at the table, and I'm kind of scanning through, and I'm just going to quickly do that with you. Start the table, equal to 1, so that's not ours. Equal to 1, so that's not ours. Equal to 1, so that's not ours. This is the only one that's equal to 0. Okay, but it doesn't quite seem to match, because ours was plus minus minus. This is plus plus minus equals 0. This is a bit of a special thing with this particular equation and surface. It's okay, but it doesn't on the surface here right now seem okay, maybe because this is plus plus minus terms equals 0. Let me go back to the question up above and show you why it is okay. But remember, in the table, it was plus plus minus. Plus plus minus in the table. So here we are back at this problem, and it seems like we might have an issue, but we don't. The table, remember the terms were plus, plus, minus. It doesn't seem to jibe with ours, which are plus, minus, minus. But also remember the whole name of this game is taking a given equation and doing equation things to it, tricks, algebraic tricks with 1/4 and stuff like that. Or divide through by -4 in an earlier problem to get it to match what's in the table. So there's one more trick we need to do here, which is multiply through by -1. So we can multiply everything by -1, and we get y squared, -1, negative y squared over 1 squared, and then plus, because we're multiplying all these terms by -1. And plus x squared over 1/2 squared, and then a plus z squared over 1/3 squared, and the other side is 0 times -1, which is still 0. So this will be y squared over 1/2 squared plus z squared over 1/3 squared minus y squared over 1 squared equals 0. So keep that form in mind. Now it is plus, plus, minus. I'm going to scoot back to the table for just a moment, and then we'll be done with this one. So here we are looking at the table, and this equation matches ours. Now we've managed to adjust ours, if you will, into this form. Okay, the variables are permuted differently, but that's okay. Ours would be an elliptic cone like this. And so that's what we're going to be looking for in our question, this shape. And here we are back at the question, which was to match this equation with its graph. We went through all the rigmarole with the equation, and we saw from the table that it should be an elliptic cone, which is this picture. All right, this is question 4. 4x squared minus y squared plus 4z equals 0. So actually the first thing you want to look for in these, matching these equations with their graphs, is one of the variables not squared? Because that's two different cases in the table of 6 types of surfaces. And in that situation, when one of the variables is not squared, what you want to do is solve the equation for that variable. So let's solve this one for z. Now my first step in solving is I've left the 4z where he is, and I've moved the other two terms to the other side and changed their sign. And so 4z equals y squared minus 4x squared. Now let's divide through by 4. That'll give us z equals y squared over 4 minus x squared. Or we can put x squared over 1 because we're familiar with the forms in the table. Now I'm going to go down to the table and look. It's the last two entries in the list of 6 which have one of the variables being solved for not squared. And here's ours. This matches the form that we just got down to in our example. We have z equals, and the other two terms have the variable squared and a minus in between them. And it's called a hyperbolic paraboloid. And the other one where the z is solved for, or some variable, doesn't have to be z, is raised to the first power only, and you solve for it is called the elliptic paraboloid. So ours is, though, a hyperbolic paraboloid.